Okay. Good morning, good afternoon, good night, wherever you are, and warmly welcome to session P8 on novel approaches in software engineering education. In this session, we will have 5 papers, and without further ado, we will get started with the first paper, who is entitled Enriching Programming Student Feedback with Audio Comments. It's a paper by Jake Renzella and Andrew Kane from Deakin University, and it will be presented by Jake Renzella. Jake Renzella is a PhD candidate in the School of Information Technology at Deakin University, Australia. His research focus is on computer science education, specifically in the intersection of how artificial intelligence can support teaching and learning in introductory computing in higher education. Jake is also a software engineer at the Applied Institute of Artificial Intelligence and a maintainer of the Doubtfire on-track learning management system project. And with that introduction, Jake, take it away.
Thank you, Caspar. So I'm just trying to share my screen right now. Here we go. So hopefully everyone can see the slides now. Thanks for coming to the presentation, Enriching Programming Student Feedback with Audio Comments. Let's get straight into it. So the research goals for this project were to address the growing online cohort pain points, I think especially pertinent now with the recent shift due to the COVID pandemic, to improve the quality of formative feedback in introductory programming, support students, and to investigate the efficiencies of providing audio feedback, whether or not it's sustainable and efficient. So exploring the literature on audio feedback, there's many studies on audio feedback that identify many benefits. However, there are very few where it's looked at in the context of introductory programming education. And in a lot of those papers, the implementation details we perceived may have impaired the analysis and the quality of the tools. So for example, many studies didn't have a learning management system that had audio implementation, so they had to use external audio recorders, send files via emails, etc. And we're looking to validate the literature on audio feedback in programming rather than all the different domains that it's covered in. So as a quick context and how we implemented this system, our introductory unit, which is a fairly large one in Australia, uses this system known as Doubtfire as a learning management platform. You can see the link to the platform just here. And there's 3 main components: the task inbox, which is where the teachers access anything that needs to come to their attention, such as a new submission or anything like that. Then we have the task submission panel. So this is where you would see, for example, your students' code that they uploaded in the form of a PDF where you can scroll it. And finally, and most importantly, is the task discussion panel. So this is where you're communicating with your students, providing feedback. Traditionally, this was just supporting text. And this is where we implemented a native audio recording and playback system to facilitate providing that feedback. And this system was cross-platform and cross-browser. And actually to do this was fairly difficult, so no plugins are required. It supports the native browser's API, and actually had to implement our own media recorder API to ensure that all browsers could interop. And because we did that work, it meant that the audio recording and playback was really fast. You don't have to launch another program, download any files. I think lately this is getting more normal, but even recently, many systems that have audio recording rely on plugins and things like that. So the methodology of the actual study. We looked at all our introductory programming submissions that we'd received on the platform over a number of years, and we tried to categorize them into a series of categories on the type of feedback that our tutors were providing back to the student. So we came up with 8. It's a fairly informal categorization, and it does apply only to us at this stage. However, we do feel that this is a good basis for the different types of feedback that anyone who's in higher education providing programming feedback at an introductory level. So for example, you might have submissions that have no problem at all. However, you could have submissions where the student is seeking clarification on concepts, or it's just a matter of their syntax is wrong, but the concepts are understood. So these are the kind of different ways that we give feedback. And then we recruited a number of programming tutors who had experience with the Doubtfire system. And this was just to ensure there was no bias in terms of analyzing someone getting familiar with a new system at all. And the main activity phase had three phases. So there's the pre-experiment interview, where we sought out to collect expectations towards tutors' perceptions of leaving audio feedback via their voice. The main experiment itself, which is where we had these participants go through a series of 8 submissions of those, one from each of those categories I defined earlier. The first pass, they only had access to written feedback tools that they traditionally had access to. And then the second pass, they went through another 8 series of tasks, a different series. However, this time they had access to the audio tool. And then we sought to collect their reflections. So it was a fairly long research activity. It was about 2 hours per each interviewee. And we had about 8 interviewees for this study. So the results, before anyone had access to the audio tool, 5 of the 8 participants expected audio feedback to be faster. And this is one thing we were looking at as we are scaling and approaching our larger cohorts. The time required to leave feedback can sometimes get a bit tricky. So if audio feedback can support the students in the same way, but decrease the time, that was something we were really looking for. And most participants expected audio to afford better relationship development. And this is something that's also really important, as the relationship between the student and the tutor has been shown to really support the student in learning activities, and can support ancillary things like academic integrity, actually. From the main result, we found across the 8 categories that we identified a range in efficiency gain. So to leave similar feedback, in some categories, it took participants about the same amount of time, for example, category C4. However, in some categories like C3 and D1, and these are all defined in the paper, and I'll explore a bit more soon, but we did see drastic reductions in the amount of time required to leave feedback. And when we analyzed the feedback that was actually provided, in fact, the audio feedback was more thorough. And then following the main experiment, there was an increase. So 2 of the participants now came on board and thought that audio feedback was faster for them to be providing their formative feedback to students rather than written feedback. And there was also an increase, and now all participants think audio comments are better for developing relationships with their students, which was really important to us. So to discuss, when we analysed really in depth the qualitative results we got back from this study, what we found, and this was pertinent when we saw the categorization of the results, but it's not a case of audio feedback is better than written feedback for introductory programming, but a case of audio feedback being used with text feedback complement each other really well. And what I mean by this is that when we're talking about code examples in our feedback, it's better to write the code. So if your learning management system or whatever method of providing that feedback to your student is writing the code, we're trained and everyone is trained to read code. So if you're talking about a block of code, and you want to demonstrate something with that, having that code written as a comment and then providing your audio explanation on top of it seems to be the way to go. And in fact, in our experiment, we noticed several participants, and this was without any prodding or training, they were naturally doing this. So if there was something wrong with a bit of code that they were looking at in their experiment, they would type out maybe some example or some fixed solution, and then they would just go, oh, let's record it, some audio on top of this and describe it. And I think this is where
left for the presentation.
Thank you. This is where we'd get the most benefit from a tool like this. And all the participants following use of the tool suggested that it is something that they would like to do in the future. After rolling out the system to our university, we've had over 3,000 audio comments provided on the system. And we're going in further studies now, looking at ways that we can look at the broader range of students' perceptions to this. Now, this was very much focused on the tutor side and the strategy side. So thanks. That's my presentation on how we can use audio feedback to increase our connection and enrich our feedback with students. Any questions would be great. Thanks.
Okay, thank you very much, Jake, for a very, very nice presentation. Do we have any questions for the audience? Please use Clouder to type questions in the box down to your left. So far, I see no questions, but maybe I can ask one, Jake. Did you
Sure.
consider the fact that audio feedback is audio is a much richer media than text? So, for example, with respect to passing on emotion or judgment, for example, in the tone of voice would play a role. Did you consider that or receive any feedback related to that fact?
Yeah, and this is something that is in the paper more than I could fit in this presentation, but that's where, when I talk about relationship development, I think that's really what I'm talking about. And I actually gave some anecdotes in the paper as well, but I've had many cases of where students, you're providing feedback to them, we're providing feedback all day, and our feedback can get a bit cold. And we're not feeling that way, you know, we're not trying to be rude, but sometimes when you just tell a student to fix something small, they can read that, and that's the only interaction they've had with you for a month potentially. But when you're providing your feedback via your voice, they're hearing that you're in a good mood, you want them to succeed, and that there's a human on the other end of this computer that's providing them feedback, not just some written robot. So definitely the tone and the way that we can communicate is just so much richer. And I really would like to see it become more of a standard way that we give the feedback to all students, really. Exactly.
Okay, thank you. And then if we take one question here from Clouder, if you need to combine written and audio, doesn't this increase effort?
Well, it may, but keep in mind that when you're providing that written feedback, you might have to write an entire message, you know, hi students, this looked good, this didn't look good. So you're typing more, but when you're using them in conjunction, you can just type the bare bones, maybe copy paste a bit of code that you're trying to demonstrate, change something. And then while you're doing that, you could even be potentially, I mean, in the way our implementation works, you can leave both at the same time. So I don't necessarily see it as that they aggregate completely. However, of course, yeah, the more touch points you have, a little bit more time it's going to have. But even in those results we had, and while those results are fairly limited, some of those audio reduction in times were with the participant leaving both the written and the audio feedback. So yeah, it's a matter of seeing what works for your team.
Sorry, I have to cut you off there.
No, all good.
Thank you so much, Jake, for the presentation. And we will move on to our second paper, which is a paper by Michael Milanovic and Jeremy Bradbury from Ontario Tech University in Canada. And the paper is called Gidget ML, an adaptive serious game for enhancing first-year programming labs. The paper will be given by Michael Milanovic, who is a PhD candidate in the Software Quality Research Lab under the supervision of Dr. Jeremy Bradbury. He received his master's in computer science in 2015 from Ontario Tech, and his BSc in computer science in 2013 from the University of Toronto. His research focuses on game-based learning in computer science education and is part of the Serious Games for Computer Science project in the SQR lab. So Michael, we are looking forward to your presentation.
Thank you so much. Let me just share my screen. Okay, I hope that looks good. Thank you for coming here. I'm presenting this work that is done by myself and my co-author, Dr. Jeremy Bradbury, so let's jump right into it. The problem that we're looking at tackling has to do with the literature and the development of serious programming games. These are games that are used for education, typically designed primarily as games, but the main concept behind them is that we want to use them as a way to engage students, to motivate them, to want to get involved with computer science, sometimes from a very early age. The challenge with many of these games is that they are designed in such a way that the gameplay is very sequential. No matter who you are, if you are playing a game, you are presented with the same series of levels that you're expected to complete from start to finish, regardless of whether or not you are competent in computer science or computer programming. This is a challenge for introductory programming classes, which may have students coming from a very diverse set of backgrounds and skills. There may be the case that some students in the class have extensive programming experience, while others may have never written a piece of code in their life. So these games have some challenges when it comes to targeting their audience towards students from a diverse set of backgrounds. So what do we do about this? Our solution is an automated adaptive approach to taking these existing games and modifying them using non-invasive player assessments. We look at how someone is doing in the game and use that performance data as a metric to determine are they highly competent, maybe medium level of competence, or a low level of competence with respect to computer programming. This methodology has been published in the past, and we've implemented this into the study that I'm going to talk about today. So how do we assess if that approach is actually viable? Well, we need to ask two very important questions. First off, is the game that we're adapting actually suitable for adaptation? Will it benefit from us doing that? And second of all, does the adaptive version have an effect on a learner's level, on adapting to a learner's level of competency? Will it engage students to adapt an existing game? So the game that we chose for this was developed by Amy Ko and Michael Lee and is called Gidget. It involves a little robotic character who is navigating the world to save animals from environmental hazards. The way that you play through this game is by writing code instructions, which are written in a very simple language, instructing the Gidget character to move around, collect items, and solve different problems. The obstacles in the game and the goals that need to be accomplished are listed to the student in the bottom left. And every level includes a set of starter code that always has at least something wrong. So in this very simple example, Gidget probably is supposed to go to the left, but the instructions are telling it to go to the right, which is not what you want to see. So the game tries to teach debugging by showing someone what happens when you run the wrong code and encouraging them to correct it to make a valid solution. This game has been the subject of a number of different research studies in the past, which is one of the reasons that we selected it as a possible candidate for our adaptation methodology. So the methodology that we have follows this sort of timeline with regards to how someone might play the Gidget game with the adaptation involved. The first step is to take some of the tasks that are already in the game, some of the levels that are already present, and leaving them as they are, collect data from students as they play through the levels in the game. Once we've collected enough data, we can initialize a model that tells us what is the level of competence of a given learner. Using that model, we then adapt successive tasks to accommodate their level of competency. So someone who is seen as being more competent might get a more challenging level than someone who is at a lower level of competence. We then continue to measure their behavior as they perform on these different tasks and continuously update the player model to see what changes happen as they go through the game. And this is sort of a loop that happens over time until they reach the end of the level. If you're interested, Gidget is available on GitHub. You can search for it yourself or just ask me after. I can send you a link. So what do these adaptations look like? What changes do we actually make to the game? So here is one example of a piece of starter code that's been modified based on the level of competence of the learner. So on the left side, for a low competence learner, we give them the code that's almost completely correct with just a very small mistake in it. Whereas on the right side, a high competence learner might need to add a substantial more amount of code to what's already there, as well as fixing errors that are already present. So we ran an experimental design using our adaptive version of the game in comparison with the original version of Gidget that was only modified to add logging capabilities. In the first half of our study, we had participants play the first non-adaptive Gidget game for 2.5 hours, followed by demographics and game experience questionnaires to tell us what a little bit about themselves as well as what they thought about the game from a qualitative perspective. All of the data we collected from that first study was then used to design Gidget ML, our adaptive version of the game, where we combined all of the data from our first study, as well as data from any successive participant to continuously adapt the gameplay in Gidget ML for each participant going forward. Each of these participants also completed the same questionnaires as those did in the first study. So in terms of our evaluation, we had 100 undergraduate students enrolled in a first-year programming course. The average age of these students was 18.5. For gender distribution, we had 81 men, 12 women, and 7 who were either transgendered or had no gender specified, which we just grouped together for anonymity purposes. In terms of programming experience among these participants, 23% had never taken a programming course before, and 30% had never written a program before. We ran our study in our first week of labs in the course across 6 different sections, the first half completing the non-adaptive Gidget game, the second completing Gidget ML. So we looked at 2 different variables in terms of our adaptation. The first that we looked at was failure rate. So in comparison to other students, how frequent, what was the variance with how a single participant might fail on different levels. Would they fail one level very many times but be perfectly okay on the next one? Or would they be more consistent through all of them, maybe making 2 mistakes per level or something like that? And what we saw is that for those playing the non-adaptive version of Gidget, they had a very high variance when it came to how often they would fail on a given level. This variance decreased significantly when we gave participants Gidget ML instead. And so you can sort of see this line going down as the variance in failures decreased as we continued to add more and more data, to the point that in our final lab session had the lowest variance among all the groups. We also looked at energy usage, which in other words is how efficient were the solutions, how quickly could they get a solution working, requiring the fewest amount of steps from the Gidget character. And we saw the exact same sort of trend, where there was a very high variance among those playing the non-adaptive version of Gidget, while those who played the adaptive version had a lower variance, which continued to decrease as we added more data in to improve our algorithm for adaptation. So in conclusion, we felt that Gidget does have the potential to benefit from adaptation. As we asked in our first research question, learners showed that they had a very high level of variance, both in their failure rate as well as their efficiency of their solutions. And Gidget ML, our adaptive version of the game, significantly decreased that variance among those who played it. As we collected more data, this variance decreased over time, and we used that as our indicator to say that Gidget ML can adapt to a player's level of competence. So in terms of future work that we're looking at continuing along these lines, we're looking at applying that same adaptive methodology to other CS serious games. In particular, those that have a different style of gameplay than Gidget. It happens to follow a very specific style where you have to write code to solve a given problem, but there may be other games with a more exploratory nature that this methodology might be better suited for. In addition, we're looking at other data sources for adaptation besides just, in this case, failure rate and efficiency. Looking at things like biometric data that we could collect from users, as well as their eye tracking data, might give us a little bit more insight into their level of competence. And finally, what are some of the other strategies that we can use for adaptation? What would happen if we tried adapting during levels instead of between levels, as an example? So thank you for coming to my presentation. As a new PhD student, these things are always pretty important to me. And if you're looking for a collaboration, feel free to message me in the ICSI chat. Thank you so much.
Thank you very much, Michael, for the presentation. And we have time for at least one question. So we have one here in Clouder. You compared students using Gidget ML and without. Did you notice any difference in final coding skills? So if the task was too simple, did that reduce competency?
So we didn't look particularly at coding skills for this game. The main reason for that is Gidget itself was originally designed in particular to limit the effects of syntax on debugging as a problem-solving skill. So the original designers actually of the game decided that coding skill in particular was not something they were going to focus on. It was more on the debugging side of things, and especially removed from correct syntax. Things like if statements and such aren't actually present in this game. It's a much more simplified type of coding that wouldn't really be appropriate for that kind of measurement.
Okay, and then there's a quick question here. Is this a kind of reinforcement learning?
Is this a kind of reinforcement learning? I wouldn't really say it's something like that. This, I think, is something that, again, it was originally designed to be introduced to someone with no coding experience whatsoever. So I think this might be a good introduction for someone into the world of coding, into the world of debugging. But I think there needs to be something built on top of this, whereas this does not, I think, amplify skills that you might be taught ahead of time. This is intended for someone who's picking things up for the first time.
Okay, great. Thank you very much, Michael, for the presentation and for answering the questions. We'll move on to our third presentation. It's a paper by José Benedetto and Jaime Navan from the Pontifical Catholic University of Chile. It's called Exploiting Group Shuffling Dynamics to Convey the Importance of Good Software Design. And this is an experience report, so we have 6 minutes for it. The paper will be given by José Benedetto, who is an assistant professor at the Pontifical Catholic University of Chile. His research interests lie in applied software development and mobile cloud computing. His previous professional industry experience includes several startups in Chile as well as the Android team at Google in California. And with that, Jose, take it away.
Thank you, Casper. Let me share the screen. Alrighty, it seems we're good to go. There we go. Let's start the presentation. So, ladies and gentlemen, thank you all for joining us today. So, as Casper said, my name is Jose Ignacio Benedetto, an assistant professor at the Pontifical Catholic University of Chile. And today I will be sharing with you our experience when implementing a new course methodology at an undergraduate level course of applied software design. First, I would like to start this presentation with the motivation behind our research. The software development lifecycle defines several activities. Amongst these, I would like to focus on those related to design. Software design activities are very particular in that they are often quite laborious and notorious for not producing any immediate tangible benefit. Nevertheless, there is no question about it amongst professional software engineers. Design is important, and the consequences of omitting a good design in the interest of time can end up being very costly. Undergrad students, however, are harder to convince. Why does this happen? This is due to the massive gap between software projects in industry and academia. In the industry, software projects tend to be highly complex and may end up taking years to complete. Here, no modeling can only lead to spaghetti code and disaster. In college, things are different. Projects are much smaller and simpler. Therefore, the cost of omitting design ends up being negligible. Thus, we propose to spice things up to fix this misconception. Introducing team shuffling. Let's have a project where teams would no longer be fixed and have different instances along the semester where groups will be forced to choose one amongst themselves to leave the group and join a different one. We refer to these people as newcomers. Team shuffling changes everything. Design artifacts become pivotal in facilitating a newcomer's induction. Technical debt and bad programming practices become relevant, as whoever is responsible may suddenly leave the group in the future and leave everyone else to deal with the mess. Thus, students gain a whole new appreciation for good design practices. Team shuffling also allows us to emulate a very important reality of the software development industry, high turnover rates and its consequences. At the software design class at our university, we test our students along two different dimensions: theoretical concepts through written tests and applied software design through a semester-long project. We will now be focusing on the latter. The project consists of a relatively complex web application that has to be done in groups of up to 4 people. Grading is performed along 4 different cycles, each lasting about 1 month. At the beginning, the focus lies on the model, only shifting towards the implementation towards the end. Team shuffling takes place at the end of cycles 2 and 3. Grades are assigned by both the academic team and the students' teammates to ensure the largest amount of feedback. Co-evaluations in particular are very important for solving a small caveat that arises when implementing team shuffling dynamics, and that is ensuring fairness. You see, when switching teammates around, it can happen that a student from a high-performing group ends up with a group of less skilled people, therefore negatively affecting his grade. The opposite is also a possibility. To ensure fairness, we use the following formula when grading. This way, if a high-performance student gets stuck in a lower-performing group, he gets to keep the grade of his original group, while in the latter case, if a student does nothing and gets only bad co-evaluations, he may still end up failing the class. If you're interested in applying this methodology in one of your classes, we invite you to read our short paper to learn more. Thus, we have arrived at the end of the presentation. I thank you all for your time, and I wish you all a good experience at PIXE this year. Thank you.
Thank you very much, Jose. And I think we can take one question if we have any.
Of course.
So we have a question here. Did students perceive this as fair?
So comments were various. On the first hand, there was a lot of anxiety at first because this was the first time we applied the methodology. However, students were unanimous in that at the very least, the grading system was spectacular. I got nothing but positive comments regarding it because of the caveats I mentioned. Both of them actually took place. And of course, students who did nothing, they got a bad evaluation and they totally deserved it. And those who ran into issues for moving on to teams with lower performance, they did not saw a dip in their grades. So they were satisfied in the end as well.
Okay, thank you very much, Jose. And we will move on now to the next paper. We will move from Chile to Australia. And the next paper is by Laura Tubino, Andrew Kane, Zhangyi Snyder, Dahanjay Tiruvadu, Niroshinia Fernando, all of them from Deakin University. It's called Authentic Individual Assessment for Team-Based Software Engineering Projects. And the paper will be given by Zhangyi, who is a professor in software engineering and also the deputy head of school at Deakin University School of Information Technology. His research lies in the general area of reliable software systems and positioned in the intersection of software engineering and computer science. Furthermore, he has a significant interest in computing education, especially the influence and applicability of software development processes in final year capstone projects. So, Zhangyi, we're looking forward to your presentation.
Thank you very much, Casper. And just a second so that I can share my screen with everybody. I hope everybody can see that. As Casper said, this is joint work with a number of colleagues of mine at the School of Information Technology. And in a way, it's the first of two presentations, because the presentation after that, given by colleague Peter Eklund, talks about a similar context. Now, in our school, we're running capstone projects basically across all of our IT degrees. And running capstone projects does give us a certain number of challenges. What I want to specifically focus on in this presentation is assessment, or more specifically, equitable assessment, so that students do get assessed in such a way that the context of the project team they're working in is reduced as much as possible. What we do not want is students that are performing really well being stuck in a low-performing team and getting penalized for that, but also the other way around, students that are sort of cruising along, but happen to be in a really well-performing team, getting a great grade that they probably do not deserve. Now, given the short amount of time I have, I can't really go into a lot of detail, but we've reviewed quite a bit in this space, and some of that is summarized in our paper. And we came to the conclusion that we probably need to focus more on individual than team-based assessment. So how do we go about doing that? First of all, we sort of thought, okay, what are the key areas or key dimensions we want our students to be assessed in? What does a student in a project setting need to demonstrate? And we came up with 12 different categories that we grouped basically into a basic, core, and advanced groups. The basic group deals with compliance. So we want our students to engage with the project. We want them to attend whenever they need to attend. They have to be accountable for the work they are doing. And they also have to demonstrate professional behavior to us. In the core or enactic group, we focus on a mix of soft and IT skills. So we want students to demonstrate to us how they can communicate, both within a group, but also to other project stakeholders, how they work together as a team. We do not want to encourage heroes that do all the work themselves and do not work with others in the team, that they do follow a reasonably well-defined process. They do, at the end, produce some outcomes, depending on what project there is. There could be a number of deliverables, and that they ultimately demonstrate IT skills to us. Writing documentation alone is not necessarily demonstrating IT skills. And finally, at the advanced level, we want students to be able to assess themselves. Are they aware of themselves and the others in the context of their team? Can they manage a project? And the reason why that's under adaptability is all of our projects are different, so they have to adapt the way they run the project to the specific needs, and there generally isn't a one-size-fits-all solution. And last but not least, we want to see how students help each other out. So what kind of mentoring can they do? And that's sort of one dimension of our assessment. The other thing we looked at, what type of students do we actually have in our classes? And we came up with a number of personas that define certain traits of behavior. Now we've got Fred Flintstone at the left here. That is a student that doesn't care less about the project, does an absolute bare minimum, and in many instances doesn't even show up. And we've probably all seen students of that nature. Then we've got Peter Pan, a student that can do work when he is asked to do that. He may need a little bit of guidance, but it is not a student that is proactive. So he doesn't seek work. He doesn't necessarily help others out. He just does what he is told and is satisfied with that. Now, the next level up, we've got the cat from Alice in Wonderland, who can perform their role in the project. A student of that nature is above what Peter Pan demonstrates. He can lead small parts of the project, shows a certain level of proactiveness, but basically can perform their role in the team. And then very much at the end, we've got Daffy Duck, who is the leader of the team. He can not only see himself in the team and what needs to be done, but he can also help others out. He knows what the strengths and weaknesses of the other students are and can allocate work according to those strengths and weaknesses, but also according to some learning objectives that certain students need to demonstrate. Now, we don't want to restrict ourselves necessarily to those 4 types of personas. In the Australian context, excuse me, they correspond to fail, pass, credit, and distinction grades. I do know in other areas, there are different type of grading categories, and I think it's easily possible to create personas for the different type of grading categories that you're operating in at another university. What we explicitly left out is the highest possible grade, which is a high distinction. I'll come back to that in a second. What we then do, we create an assessment rubric where at one dimension, we've got our personas, and at the other dimension, we've got our assessment criteria. So the 4 elements in core, 5 in basic, and 3 in advanced. And now for each persona and for each assessment criteria, we have descriptors that define what expectation we have for a persona at that particular assessment criteria. Now, the more you move from the left to the right, those expectations grow. So clearly, Daffy Duck has to demonstrate more than Peter Pan does. What we also ensure is that the higher level descriptors imply achievement of the lower level descriptors. So if a student operates at the cat level in all 4 core areas, that student by implication also operates at the Peter Pan level across those 4 dimensions. What we want to do, we want to stretch our students. So our highest level of achievement, Elastigirl, kind of indicates that students have to be stretched to achieve that. And not too many students should operate at that level. They have to demonstrate some form of excellence to us. And we think in compliance, you can't really demonstrate excellence. So that's why we have a big red cross there. Now, the way we assess students is they have to demonstrate that they meet all 12 criteria for a particular persona. So it is not that we're averaging things magically out. So if somebody in our context wants a credit, that student needs to demonstrate the achievement of the 12 criteria that is listed under the cat. If they operate in some of them a bit higher, that is okay. The moment they do not meet all the 12 criteria, they immediately go 1 grade category down. Some academic judgment can be applied, but most of the time, if a student doesn't meet all 12 criteria, they do not deserve that particular grade category. Now, how do we put that in operation? Students tell us where they think they're at, and we then double check that there is sufficient project evidence that they operate at that level. So we have a number of regular checkpoints throughout the trimester where we provide them guidance or feedback on where they're at and what they possibly need to improve. And students are only assessed at the very, very end of our teaching period. This encourages them to try things out, make mistakes, but hopefully learn from these mistakes. Now, there is a lot more detail in our paper, and I want to conclude with that, and I'm more than happy to take a few questions.
Okay, Shangui, thank you very much for the presentation, and we do have time for a couple of questions. So, Shangui, if I start, so I find this really interesting. One thing we've learned from our projects is that we have very limited contact with the students as teachers. So we find it rather difficult to do individual assessments. And you said here you have this evidence. So could you perhaps explain a little bit more in detail how you think you're able to actually do individual assessment of how students perform in projects based upon typically quite limited contact?
So the teaching staff that ultimately do the assessment, they have at least weekly contact with the students. So we're mandating that there is at least one meeting where teaching staff and all the students in a team come together, and students are asked to present where they're at, and we can then ask appropriate questions. Students are told how to collect evidence across the trimester. And as I said, there are a number of checkpoints where they get feedback on how well they're demonstrating a case to us, what grade they should be deserving. And the combination of those two gives us a reasonably good handle where we think students are at.
Okay, we have a couple of more questions. So the first one is, I missed how the team component was involved. Can they do well if the rest of the team is terrible?
Absolutely. And I think that's one of the key things why we came up with that individual assessment. Individuals that do well, but by accident end up in a team where everybody else is doing the bare minimum, they can demonstrate to us that they are excelling and therefore can get a great grade.
Okay, thank you very much, Shangui.
It's about demonstrating individual achievement in the context of teamwork.
Thank you. And with that, I think we have to close this paper and move on to our last paper of this session. This is a paper from the same university. It's called Adopting Industry Agile Practices in Large-Scale Capstone Education. And it's a paper written by Shangui Schneider, Peter Eklund, Kevin Lee, Fei Chen, and Andrew Kane, and Mohammed Abelrazek. And the paper will be given by Peter Eklund, who is a professor of AI and machine learning at Deakin University School of Information Technology. Peter has been engaged with group-based student education for more than 10 years and is one of the team of more than a dozen academic staff that have contributed to capstone education at Deakin in Melbourne, Australia. So, Peter, we're looking forward to an interesting presentation.
Thank you, Caspar. Can you see my slides?
We can.
Excellent. Thank you for the introduction. This talk is a continuation from Jean-Guy's talk about assessment of capstones. And in particular, we were motivated in 2018 to reorganize and remodel 4 capstone units that were experiencing a number of problems, including grade inflation due to excessively process-based assessment, poor and unsophisticated project outcomes, high attrition and dropout rates, and generally dissatisfaction amongst the stakeholders, the client, the student, and the supervisors. To give set some context, Deakin is a multi-campus Australian public university, and this presentation relates to activities at Deakin's largest campus in Burwood, which is 12 kilometres east of the city of Melbourne. The School of Information Technology offers 5 undergraduate degrees in computer science, in cybersecurity, software engineering, artificial intelligence, and information technology, representing 10 ICT discipline or specialisation areas. It also offers Masters by Coursework degrees in information technology, both conversion and extension programs, and a master's degree in data science. The school has more than 100 academic faculty and about the same number of PhD students. Now, the School of Information Technology at Deakin is very large, even by Australian teaching standards. In 2019, there were 2,500 full-time equivalent students at our Burwood campus, and because the capstone units are a compulsory feature of all our courses, as Jean-Guy mentioned, we figure that about 1,000 students at both undergraduate and postgraduate level are enrolled in one of the 4 capstone units in any single teaching semester. In addition, there are also students studying in our cloud campus, that is to say, online, and many student teams therefore consist of blended online and on-campus learners. As well as the challenge of scale, previous experience with capstone had proven unsatisfactory, as I had mentioned. So just to, I mentioned some of the reasons for the redesign, but just to give some design parameters. What are we trying to achieve here? Well, firstly, we aim for a relevant industry experience. That is an experience that is similar to practices in the workplace. We want authentic learning experience, namely that students learn something new. We're looking for a continuity of learning experience so that projects have a life of their own beyond a single teaching period. We want a scalability of the approach so that the model is sustainable and supportable for hundreds of students. And we also need effective student support so that there's appropriate resourcing through a support matrix so that students can have access to the help they need when they need it. So our paper contains an extensive survey of prior art in university capstone organisation experience, but in rethinking how the capstone experience could be improved, we turned to agile and scalable models from the ICT industry. There, under ideal circumstances, a matrix of support relationships organically evolves from the organisational model. Now, the Spotify tribe and squads model seemed like a good starting point and provides the inspiration for our own model. Now, some adjustments are necessary in the educational context. This slide shows how in 2019, we operated with a model where we had a single academic supervisor per squad, but we found that the levels of engagement of supervisors with students was somewhat uneven. Some supervisors more enthusiastic than others. In 2020, we successfully experimented with an academic and industry mentor model, who as a pair provide advice to 4 different squads in a single timetabled 3-hour block each week. So a single tribe leader, who's a full-time faculty member, serves as a contact point for the squads in a tribe and acts as an intermediary to the external client, the product owner. Another feature of the resourcing is the provision of professional technical support personnel. And these are full stack developers from the software engineering industry. We hire in for 4 to 8 hours a week to work as a help hub. Students can book appointments with the technical staff to ask questions or seek design advice. In addition, as mentioned, we wanted to achieve continuous improvement of the product line over time, and this necessitates doing something that's really quite bold. So what is it that's bold? Well, the squads are blended with students from both capstone units. A squad continuity is addressed by considering students in the first semester of the capstone as C1 students. It says junior students in the slide, although we never refer to them as junior or senior. And students in the second capstone unit known as C2 students, or in the slide, senior students. Over the time since we've started the model, students have transitioned through their squads from C1 to C2. And once they attain familiarity with the project, they can mentor the newly arriving C1 students. The result has been increasingly more sophisticated product lines as the squads continually refresh their members We think this evolving and dynamic model is a good representation of ICT industry practice, and it also promotes leadership and peer mentoring between one generation of students to the next. So the idea here is that a single tribe can have multiple squads that respond to the same or different aspects of the product line, which continuously improves. In 2020, there were 18 tribes and approximately 615 undergraduate students, 660 postgraduate students. Now, there's a lot of overlap in the cohort because many of the students who are in C1 become C2 students. So they obviously should only be counted once, and here they're counted twice. But in total, there were 65 undergraduate squads and 75 postgraduate squads, a total of 140 squads in 2020. So Jean-Guy's covered assessment, but in essence, what it involves is 3 sprint reviews through the 12-week teaching period. But we've also experimented with the Spotify chapter idea, offering professional development workshops on a variety of generic software engineering tools, such as GitHub, Trello, JavaScript libraries like React.js, unified programming, wireframing, storyboarding, ideation, and so on. Now, another key ingredient, both pre and post-corona, is the physical space intended to make a sticky campus, a campus that students want to be on. We created what we call the Discovery Lab, which is 800 square meters of dedicated capstone student space. And this is an important feature of our model, creating a co-working space with bookable presentation rooms, video conferencing, a boardroom, breakout areas, and a large communal kitchen. And this simulates a high quality tech industry workplace. Now, this results in a working environment that allows our students to meet with each other, their academic and industry mentors, the tribe leaders, and the unit chairs. A dedicated administrative team is also on hand so that the entire experience is professionally supported. Also, this looks expensive, right? And it is. What are the results of the spend and the effort that we've exerted here? So the full survey responses are provided in the paper of all the stakeholders. So, but in the interest of time, I focus on a single statement, and that is the capstone project units allowed me, the student, to improve my IT skills in order to get IT-related employment in the tech industry. Now, only 12 from 90 students who responded in 2019 were neutral or negative to that statement. So there really is a high student satisfaction with the capstone experience. We also observed that there's a much lower attrition rate with that's dropout rate with the new model, down 20% from the peak attrition rates in 2018, which triggered the intervention. Grade inflation is also improving. In T1 2020, and that's the teaching period that's just finished in Australia, less than 35% of students were awarded distinction or high distinction grades, the top 2 grades, and that's down from 55% in 2019 and 84% at the peak of this grade inflation in 2012. So with that, Deacon's objective is to continue to be ranked #1 Australian public university for undergraduate student experience. And that's what we were surveyed to be in 2019. And all of this work that we've done around the capstone experience is intended to maintain that position. With that, I'm open to any questions. Thank you, Caspar.
Okay, thank you very much, Peter. This looks extremely impressive. Do we have any questions from the audience? Feel free to write in Clouder. But Peter, maybe I can ask a question to get started here. I'm curious, why did you settle on the Spotify model? If you look at the industry, you also see things like logical Scrum, the LESS model, or SAFe, Scale Agile framework. Why Spotify?
Look, Caspar, it's a good question, but I think that we liked the organizational model that provided a matrix of support. So you know, the tribe leader, the squad supervisor, the squads themselves, multiple squads, the chapter concept that cuts through as well, gave us kind of, you know, a thematic educational sort of curriculum approach to the organization. So, and that's the idea here, is to try and make such a support matrix available from a resourcing point of view that students can find help in a number of different ways, depending on their needs and depending on the quality of the personal contacts that the students have with the various actors. And I think that the Spotify model seemed to suit that purpose, and its adoption in the educational environment took a bit of effort, but it was an inspiration more than an exact copy.
Okay. Thank you very much, Peter. Seems we are at, I see no questions in Clouder, so we are at the end of our session. I would like to thank all the speakers for the excellent presentations. And I also have been asked to give this closing note to say that if you have questions that you haven't asked of the presenters, you'd like to get back to them with more questions, please look for them in the lobby's video chats during the third hour. So there will be one more short 1 hour session here now. And after that, please go to the lobby to meet people there. And don't forget to visit the posters and demos today by going to Clouder's exhibit hall and joining the presenters there in their own video chats. Thank you so much for participating in this session, and I hope you enjoy the rest of the conference. Bye for now.
artifacts. So welcome to the session today on natural language artifacts. We have 3 papers today, and the first paper is going to be presented by Xiaojie, who is a PhD student at Zhejiang University, which is in a beautiful city in Hangzhou. And her research is in the area of software repository mining. And Xiaojie is going to talk to us about her work on self-admitted technical debt. You can go ahead. Xiaojie, you need to unmute. Good.
Yeah, can you hear me?
Yes.
Okay, so let's begin my talk. Hello everyone, I'm Xiaojie Ren from Zhejiang University. I'm glad to be here to introduce my work, Neural Network-Based Classification of Self-Admitted Technical Debts from Performance to Explainability and Deployability. It is cooperated with Zhengchang Xing, Xingxia, David Lo, Xinyu Wang, and Zhong Grandi. So let's begin the talk. First of all, I will introduce some background. What is technical debt and what is self-admitted technical debt? Technical debt is a metaphor to reflect the trade-off between benefits and long-term stability, and technical debt is a variant of technical debt. It's proposed to identify debt that is intentionally introduced in software development, such as temporal fix, workaround, and so on. We have found 4 characteristics of self-admitted technical debt, such as vocabulary diversity, project uniqueness, variable length, semantic variation. After observation, we also find imbalanced data is another challenge. Look at the dataset of our work. We can find that different projects have different numbers of SATD comments. We can find that the data is imbalanced. Here's our framework of our approach. First of all, we use convolutional neural network and weighted loss function to train a model, and then we use the trained model to extract to predict SATD or non-SATD, and then we use a pre-trained model to extract the key phrases. At last, we summarize the SATD patterns, and our SATD transforms. Our CNN transforms input code comments into SATD or non-SATD classification through a stack of processing layers. The convolutional neural network is not the core content of today's presentation, so I just show the architecture briefly. We explore after that, we do the deconvolution to identify key phrases. We explore the input and output traceability to extract the key phrases in the input comment that contribute most to the SATD classification. In order to extract such key phrases, we perform the following step and answer 2 questions. Let's use X1 and X7 in the fully connected layer as example. The first question is where. It means where is the location of the key phrases in the input comment. It can be seen that when we trace back, X1 represents for perhaps not, and X7 represents for not really necessary. The other question is what. It means the predicted level of each key phrases. It means SATD or not. With the formula, we can find both X1 and X7 are SATD. Thus, we can extract perhaps not and not really necessary are SATD key phrases. All the element in the fully connected layer are SATD. Can be represent key phrases with 2 steps above. In this case, we can complete the key phrase extraction. So here's the 2 research questions of our paper. One is about how do our patterns compare with human summarized SATD patterns. The other is can our patterns reveal the SATD characteristics in different projects? We use 62 manual summarized patterns as the baseline. Here's the results. It can be seen that we summarized in totally 700 SATD patterns. The figure shows the distribution of our SATD patterns of different lengths. It can be summarized that we can extract the more comprehensive SATD patterns compared with human summarized SATD patterns. The table shows the top 10 SATD patterns of different projects. We can also observe that many projects share some common SATD patterns, such as to-do, hack, and fix me. At the same time, some SATD patterns appear in only just one or two projects, such as revisit. An interesting observation, we can also find some semantic words, such as stupid. But the semantic words are different from projects to another. And then let's look at the explainability of our approach. For the given comment, we can extract the following key phrases with a high SATD probability. We highlight them in the comment and mark the comment as an SATD. So we can treat the comment as an SATD comment. This is the second research question of our approach, cross-project model generalizability. We use text mining approach as a baseline, and with two approach, one is rich training dataset and the other is limited training dataset. It can be, from the result, we can see that in the rich data setting, we use 9 projects to train the model and to evaluate the rest one. We can see that from the F1 score, our approach can improve we can improve more than 10%. And in a limited setting, we use 1 project to train the model and to evaluate the other one. From the F1 score, our approach can improve more than 40%. So for the conclusion, we have designed a propagation method to extract and highlight key phrases and SATD patterns in the code comment, which can be used to explain SATD classification results by a CNN model. And then we have conducted extensive experiments to evaluate not only performance of our approach, but also its generalizability, adaptability, as well as its explainability and of the CNN learned SATD features and patterns. So that's all my talk. Do you have any questions?
Great, thank you very much. That was an excellent talk. If anybody has any questions, please feel free to quickly post them for us to look at right now. I'll start with one question. Your approach is mining the self-admitted technical debt patterns from the repository. Have you looked at how, once you've mined these, how useful this would be and how people would really use them in a project? Are they trying to understand the extent to which technical debt has been left behind in their project? Did you talk to any users about this? Any developers, for example?
No, actually no, because it's not an empirical study, so we haven't talked to any users. But it's a good idea because the work is to help users, so we have to know what users are saying. So yeah, it's a good idea.
So, but as a follow-up to that question, you obviously, you looked at the patterns that were mined. How do you envision they would be helpful to people? How do you think they would be used by developers once you produce your results from your data mining?
Yeah, because when a project is big is very large. There are too much code inside, and so when you code something, or the code are from other people, you cannot know some technical data inside. But other people will write down some technical data inside, but you don't know. If you use our tool to mine some self-admitted technical data, you can know there is a technical data, so you can find the technical data here.
Okay, great. Thank you very much. That was a really interesting paper and an interesting piece of work.
Thank you. Thank you.
Okay, so we are now going to move on to our second paper. And the second paper is on the topic of domain-specific machine translation with recurrent neural networks for software localization. Unfortunately, the speaker of this paper is unable at the last minute to come and present the paper. And so we're going to play the video. And please feel free to write comments into the chat window. Obviously, there's not going to be anybody to actually answer these questions. But if you want to make some comments or observations, I could briefly summarize these at the end if anybody does that. So I'll ask the Zoomer to play the video for us now. Thank you.
Hello. My name is Xu Wang, one of the author of this domain-specific neural machine translation for software localization paper. And now we're gonna present our work to you guys today. So, the definition of software localization is the translation of a software interface and messages to another language plus adaptation of some formats. So, in our scenario, this basically means the translation of mobile application or software text. And the market is huge because obviously the number of softwares and mobile applications is exploding these days, and the need for translating them into another language, the need is very huge. But when we actually want to do the localization process, we may encounter some severe. So the definitional approach to do this is to hire human translators to do the translation tasks. And if you want to apply some machine translation techniques, such as using existing translation tools like Google Translate, it will not always produce a satisfactory result. And the Google translation system cannot handle those domain-specific application text, which is very common in the mobile application area. So taking this word Steam as an example, in the gaming software, in the gaming application, Steam may refer to the video game platform developed by Valve. But if you put Steam into Google Translate, it will just give you the original meaning of this word, which is vapor. So our goal here is to develop a neural machine translation system which can deliver acceptable translation for application text while still being able to handle the domain-specific words, just like the Steam word example. So to do this, we first have collected a huge data set. We've crawled around 80,000 applications from Google Play Store, which are basically all Android apps, and we extracted around 7 million training paths from those APK files, including Arabic, Chinese, French, Spanish, and Russian, which are all UN official languages, which we think is representative for the current language systems. Our model is built upon a sequence-to-sequence model, which consists of two parts. One is an RNN called encoder, another is another RNN called decoder. The encoder may take the input sequence. In our case, it is the source sentence in the source language, and it will transfer it into a context vector C. And our decoder will use this context vector plus the previous word from the input sentence to generate the output, which is, in our case, the sentence in the target language. To make our model achieve better performance, we've made several modifications. The first one is we have incorporated category information in our model. So apps belongs to different categories, maybe tools, maybe news, games, or communications, and the same word may have different meanings in applications of different categories. So taking this driver word as an example, it can mean people that drives cars. It can also mean a program that controls software in computer science field. So these are a list of categories in Android applications, and to incorporate this information in our model, we first give every category a special token, basically their name, and we append this token to the beginning of each sentence. So a sentence, this is the original sentence, and after do the appending process, we'll have a special token indicating the category of the sentence's original application. So taking our driver word as example, if this select your Wi-Fi driver sentence belongs to an application which falls into a tools category, we will just append the category token of tools category at the beginning of the sentences, and the same thing happened for this please contact your driver sentence which belongs to a transportation application. The second modification we've made is how we deal with the rare words. Rare words means that refers to words that appears only a few times in the whole corpus. It could be people's name, address, URL, and placeholders. A traditional approach to treat the rare words is just mark them as one single UNK for all rare words. But in our model, instead of simply mark them as a single UNK, we also preserve their relative position information. So look at this example. In the original sentence, there are two placeholders and a URL. So we pre-process it, not only marking them as an UNK, we also preserve its positional information. And in the translated sentence, we will have the positional UNK preserved, and then we can easily map them back to the original placeholder. The third modification we've made is to deal with those short and common sentences. So some sentences and words are very common and share almost the exactly same meaning among all applications. And these words don't have much changes in meaning, so we've developed a dictionary-based mechanics for those sentences. So when we encounter the translation of such a short and common sentence, we just look into our dictionary and instead of put them into our neural model. This will increase the efficiency and accuracy of our translation model. We've done experiments to show that our model actually achieved a better performance. The evaluation metrics, including the blue score, which is most applied metrics for evaluating translations, and we also use exact match rate, which refers to the exact match rate of our translated sentences, comparing with authored sentences. We also chose Google Translate as our baseline method. We've conducted experiments on around 20 Android applications, and our model has outperformed Google Translate in terms of both blue score and exact match rate. We've also done similar experiments on all of the 5 UN official language tests languages, and it shows that our model also outperforms Google Translate in all of those 5 languages, which means our model has the ability to generalize to other languages. That's basically what we want to present today. Thank you so much for listening.
Okay, we thank the speaker. Unfortunately, we had a recording for this one, and so I'm not going to be able to ask the question. I noticed that somebody has posted a question. Is it better to translate apps into other languages or teach people English? Which is an excellent question, and unfortunately, we won't be able to answer it now. However, if the person who asked that question looks in the paper, you can find the email of the author and maybe email them and discuss this with them. So we have one more paper presentation, and unfortunately this one is also going to be by video. So this is an unfortunate session where a couple of our speakers were unable to actually come and give their talks in person. This third presentation is on mitigating turnover with code review recommendations and the balancing expertise, workload, and knowledge distribution knowledge distribution. And the paper is going to be presented on video by Asen Mirsadi.
Hello, this is Asen Mirsadi, and the work I'm going to present has been done for my master thesis with Dr. Rigby. Our goal in this study was to use the knowledge distribution that happens during code review to reduce the risk of the work I'm going to present. At the same time, we ensure high quality reviews are provided and core developers are not overwhelmed. Well, we all know turnover is inevitable. It incurs economic costs, lowers the productivity of the team, and increases the number of defects. Mitigating turnover is also expensive. If we increase documentation, we have to change the development workflow. It takes a lot of energy and time from the team. And even with all of that in place, it's not really possible to keep everything up to date and relevant. One thing we noticed from prior work was that the code review naturally spreads knowledge. It's been shown that reviewers are heavily involved in reviewing code they have never authored, and their knowledge is gained through code review and not code authorship. So our goal was to design a review recommender that spreads knowledge among reviewers in a way that we can reduce knowledge loss from turnover. And the whole idea is based on the fact that developers naturally learn about the code they review. But who should actually do the review? Spreading knowledge by suggesting people who know nothing about files is easy. But the issue with that is you would not get expert opinions. On the other hand, if you assign expert reviewers, it would lead to knowledge concentration, so it increases the risk to turnover. So one challenge here is to find a balance between experts and learners. The other challenge is to recommend developers based on the degree of commitment they have to the project. Suggesting transient developers does not really help in reducing knowledge loss from turnover, as they are not likely to stay around. So let's see a demo of a recommender, which is named Sophia. It's a free GitHub application that you can install on your repositories. On a pull request, you ask Sophia for recommendations. Sophia then suggests potential experts and potential learners. Sophia also shows the number of files they have authored, the number of files they have reviewed, the new knowledge they gain if they perform the review, and how committed and active they have been in the project. Before explaining how we evaluate review recommenders, let's take a look at how prior work does that. They use a metric called MRR to measure how successful they are in predicting the reviewers who actually performed reviews in the past. Now, the heavy assumption here is that actual reviewers are considered as best, and the more close we can get to predicting them, it means we have a better recommender. In contrast, we evaluate the recommendations based on 3 dimensions. First is expertise. If files under review are not fully known by reviewers, you get low expertise, and without expertise, you get low quality reviews. To increase expertise, you can assign core developers to review all changes, but this strategy increases the load on the core team drastically. So we have a second metric called core workload, which measures the load on the core reviewers. And the most important to our study is called files at risk to turnover, which I explain in the next slide. So here we have a set of files in this example. This file is at risk as it's abandoned and no one in the team knows about it. This file is also at risk as it's hoarded and only its author knows about this file. If the author leaves, it becomes abandoned. And here this file is not at risk to turnover as it's known by 2 developers and it's unlikely to have both of them leave the project. So files at risk to turnover just sums up the number of hoarded and abandoned files. So We do historical simulation to understand how review recommenders perform based on expertise, core workload, and files at risk. We do it across all pull requests for all projects under study. During the simulation, we change the reviewer set of all pull requests. Here, we have the people who have done the review in reality, and here we have the recommendations for that pull request. And the top candidate is this guy. We take the top ranked person and randomly replace it with one of the actual reviewers. And then we report how using the recommendations change the outcome measures. Here is the list of projects under study. As you can see, they are fairly large. They have been around for at least 4 years, and they have a lot of pull requests. We evaluated 7 recommenders. The first one is authorship. So it's assumed if a person has made a lot of comments in the past, he would be a good reviewer. The second one is rev on rec. It assumes if a person has made a lot of reviews in the past, then he or she would be a good reviewer. The third one is called chrev, which we re-implemented because it was reported it has a better performance than the other ones. Then we have our own new recommenders. We have LearnRec, which suggests reviewers who learn most if they review the pull request. It ensures the candidates know about at least one of the files, so they have some relevant knowledge. Then we have retention rec, which scores candidates based on their commitment to the project and how likely they are to stay around. So we can get rid of transient developers whose knowledge cannot be retained in the project. Then with the turnover rec, which is the combination of learn rec and retention rec. So it suggests learners who are committed to the project. And finally, we have Sophia, which is a bifunctional recommender. Sophia looks at the pull request and asks if any of the files are at risk. If the answer is no, then we do not need to distribute knowledge and we use chrev to suggest experts. If the answer is yes and some of the files are at risk, then we use turnover rec to suggest a committed developer who learns from the review. So here we have the results. The top 3 are expertise-based recommenders, which result in knowledge concentration. You can see they all improve the expertise in all cases, but at the expense of increasing the risk to turnover. For LearnRec, we see a drastic drop in expertise. We see a significant increase in FAR, which is the result of picking transient developers. We can also see it reduces core workload. Then we have retention rec. It increases expertise significantly, their workload goes high, the files at risk to turnover reduce successfully as committed developers are suggested. Then we have turnover rec, which is similar to LearnRec in terms of expertise and similar to retention rec in terms of FAR, which is reduced by 30%. The workload change is negligible. Our results up to here show that having recommenders that excel at 1 or 2 measures is easy. The challenge is to excel at all of the 3, and that's what Sophia does. It increases expertise, the workload is constant, and reduces files at risk significantly by 28%. So to wrap it up, we introduce this new evaluation framework for review recommenders. Instead of MRR, we consider expertise, workload, and knowledge distribution. We found that no single recommendation strategy can balance all of the 3 outcome measures. As a solution, we came up with Sophia, a bifunctional recommender that achieves a balance between all outcome measures. We released Sophia as a GitHub plugin, which you can tie to your repositories. We also publish all data and code we use for research. So that's all. Thank you. Please email us your questions.
Okay, so many thanks to the speaker, Ehsan Mirsadi, in his absence. That was again another very interesting talk. If you have any questions that you would like to ask, please feel free to type them here, and they're being saved and will be sent to the authors. And in fact, for the first paper, there was one additional question that I didn't notice, and that's also going to be passed to the authors so that they can think about that. So this was a really short session on natural language artifacts. I'm really glad that all of you were able to join us for this session, and I thank the presenters. And I would like to remind you, this was mentioned at the end of the previous session, that if you want to talk further to any of the presenters from this session or the previous session or any of the parallel sessions, then you can go and join the lobby's video chat in Clouder during the 3rd hour. So that's the hour following this session. You can ask speakers questions there. And the other thing that's going on in the 3rd hour today is we have student research competition posters. We have regular posters and demos. And we also have a meet, the Ask Me Anything. So there's plenty of things for everybody to do. And I hope that you will be able to engage in some of those activities in the 3rd session. So thank you for coming to this session. And I hope you enjoy the rest of your day. Thank you.